Hi everyone. Please try this review problem before we start the actual class. Can you all hear me fine? Okay, so now I'll start off with this problem. So basically, we have Joey and Chloe and their daughter Zoe all have the same birthday. Joey is 1 year older than Chloe, and Zoe is exactly 1 year old. Today is the first of the 9 birthdays on which Chloe's age is the integral multiple of Zoe's age. What will be the sum of the 2 digits of Joey's age the next time his age is a multiple of Zoe's age? So the idea is, let's say Joey's age is x plus 1, Chloe's age is x, and Zoe's age is 1. Okay? So basically we have that. We're saying that today is the first of the 9 birthdays on which Chloe's age is the integral multiple of Zoe's age. So this seems a little bit tricky. So what does this mean? That means that on any given birthday, Chloe will be x plus k years old, and Zoe will be 1 plus k years old, right? Because Chloe will be 1x plus k, and Zoe will be 1 plus k, because after the first birthday, when there's 1 years old, k years have passed, and after the x years old, k years more have passed. So this number has to be an integer for exactly 9 values. So we're given that there are exactly 9 values for when this quantity will be an integer, right? So now what can we do? If there are exactly 9 values for when this will be an integer, how can we figure out what those 9 values are? Well, here's a clever trick to doing this problem. We can notice that this is equal to 1 plus k divided by 1 plus k plus x minus 1 divided by 1 plus k, right? Because x plus k is 1 plus k plus x minus 1. So we can clearly see that 1 plus k over 1 plus k is an integer. So in order for this quantity x plus k over 1 plus k to be an integer, and since we know that 1 plus k over 1 plus k is an integer, we need x minus 1 over 1 plus k to be an integer. So we're given that there are exactly 9 values such that x minus 1 divided by 1 plus k is an integer. And what does that mean? That means that there are 9 factors of x plus 1. The reason being that if there are 9 factors of x plus 1, then that means that, well, if there are 9 factors of x plus 1 and x minus 1, then we can see that x minus 1 has to be of the form p1 to the power of 8, or x minus 1 has to be of the form p1 squared times p2 squared. The reason is that by the factor formula learned in the AMCA classes, we see that this will have 9 factors, and this will also have 9 factors. And the reason that x minus 1 has to have 9 factors is because there's 9 birthdays such that this quantity is an integer. So that x minus 1 has to have 9 factors. Okay, so as you can see here, now we have these 2 possible values. So now what can we do? Now what more information do we have? Well, the next key piece of information is that Joey's age has 2 digits only, meaning that it cannot be a 3-digit number or more. Because if it's 100 or more, then it's too big. So we know that Joey's age has to be a 2-digit number. Well, let's look at each of the individual cases now. So for this first case, p1 to the 8, what is the minimum possible value of x minus 1? What's the smallest prime? The smallest prime is 2. So P1 to the H will be 256 at the very minimum, right? Because 2 is the smallest prime, 2 to the 8 is 256. But that's way too big, because that would mean Joey's age would be a 3-digit number. But we're given that Joey's age only has 2 digits, so that can't happen. So this case doesn't work. It's bad. Now what about this next case? Well, now we've eliminated to this next case here. Well, if it's P1 squared times P2 squared, what are the possible values for it? Well, notice that if it's P1 squared times P2 squared, what are the possible values for the primes P1 and P2? Well, the idea here is that P1 and P2 have to be 2 and 3. Because if P1 and P2 are 2 and 3, then this is equal to 2 squared times 3 squared, which is 36, right? And the reason being that no other possibility works is because let's say it was 2 and 5, the next smallest possibility, right? Because 2 and 3 are the smallest primes, 2 and 5 are like the next smallest pair of primes. So if P1 and P2 were 2 squared and 5 squared, then this would be equal to 100, right? That's way too big, because that would mean Joey's age is again a 3-digit number, which is bad because you only want 2 digits. So what does that mean? Well, that means that x minus 1 has to equal 36. No other possibilities work, meaning x has to be 37, right? Okay, so if x has to be 37, that means Joey's age has to be 38. So that means Joey's age is 38. Let me just mark in a different color. Joey's age is 38. Chloe's age is 37. And this will be 1. So that's the only possibility that actually does work based on our conditions here, right? But now look at the problem. We want to find the sum of the 2 digits of Joey's age the next time his age is a multiple of Zoe's age. So notice that 38 and 1. So just like earlier, we see that Joey's age will only be a multiple of Zoe's age if 37 is a multiple of Zoe's age. Because the difference in their ages is 37. The difference in Joey's minus Zoe's ages is 38 minus 1 or 37. So the difference of its ages has to be a multiple of Zoe's age in order for it to work. So what are the 2 factors of 37? Those are either going to be 1 and 37. So those are the 2 possible values of Zoe's age for this condition here in the problem. The condition here that Joey's age next time is a multiple of Zoe's age. This will only be true if it's an integer, it's a factor of 37, so 1 or 37. We already see that Zoe's age is 1 is the current value. So we want to find the next time Joey's age will be a multiple of Zoe's age. So the next time Zoe's age will be a multiple of Zoe's age is if well, Zoe's age is 37 and Joey's age is 74. And we can see that the difference of 37 between their ages is constant, so we're good. And the sum of the 2 digits of Zoe's ages is just going to be 7 plus 4 or 11. And that's the answer for this problem. Okay, so now let's move on to the topic for today. So for those of you new here who just joined, today we're going to be talking about GCD LCM, modular arithmetic, and Diophantine equations. Okay, so we can see here that we have this long equation. A times B plus 63 equal to 20 times LCM AB plus 12 times the GCD of AB. Okay, so in this problem, I'm probably going to be writing LCM and GCD so many times. So just for a shorthand notation, I'm going to say L is LCM. Let's do capital L. So let's just say capital L is LCM of A and B. Let's say G is the GCD of A and B, because I'm gonna have to write GCD many times, so it's just an easy shortcut that I can use. So let me just plop that into our equation really quickly. So if I make those substitutions just to make it easier to write when I'm dealing with the whole problem. So I'm just gonna replace the LCM with L and the GCD with G. So now we're left with 20L plus 12G. So now what? Well, now we have a bunch of variables here. So we want to try to use less problems. So we want to use less variables. So in order to use less variables, what we can notice is that AB is just going to be the LCM times the GCD. So let's just say that this is equal to LCM times GCD plus 63 is just going to be equal to 20L times plus 12G. Because remember, we learned that the LCM times the GCD is just equal to the product of the numbers. Remember learning that in the other class. So 20L plus 12G. And from here, we can subtract 20L and 12G from both sides to get LG minus 20L minus 12G plus 63 is 0. And then from here, we can use Simon's favorite factoring trick to get this will just be L minus 12, since we need a negative 12g term. And then we also multiply that by g minus 20. Because again, we need a negative 20 times L or negative 20L term. But now, or sorry, that was a bit of let me just re-explain that using more detail. So basically what we need to do is now we have an L minus 12 and a G minus 20 term. But as you can see here, now we're adding 240 to both sides. So now from here, we have 63 is equal to 0 plus 240. Because we added 240 to the left-hand side, so you have to add 240 to the right-hand side too. And then simplifying this whole equation, we get L minus 12 times G minus 20 is going to be equal to 177, right? And then from here to see the possibilities, well, we can either have 1 and 177, 3 and 59, 59 and 3, and 177 and 1. And this gives us that L can be 13, G can be 197, L equals to 15, G equals to 79, L equals to 71, G equals to 23, L equals to 189, G equals to 21, but not all these cases will work. Basically, the idea here is that, well, the LCM has to be multiple of the GCD, because the GCD of a number has to be a factor of the LCM, since the GCD contains the common factors and the LCM contains the overall all the factors. So basically, the idea here is that the LCM is all the factors, GCD is only some of the factors. So the LCM has to be the multiple of the GCD. So from here, we can see that the only case that will work is this last case. All these three cases won't work, since in these three cases, the LCM is not a multiple of the GCD. So then from here, we can see if the LCM is 189 and the GCD is 21, both of them have to have factors of 21, right? And if both of them have to have at least a factor of 21. But then in order for the LCM to be 189, one of them has to have an additional factor of 9 in them. So that means we know that one of the numbers has to be 189 and the other number has to still have a factor of 21. So from here, you can see the possibilities are just 189, 21, 189, 63, 189, 189, or we can also just flip them up. So, but we can see from here that this possibility, the last two possibilities don't work. Since in this possibility, the GCD is not 21, but it's 63. And this possibility, GCD is not 21, but it's 189. So we cross these two possibilities out. So we see that the only possibility is that the LCM is 189 and the GCD is 21, right? So from here, we can see the possible values such that this will actually be true are, we want to find how many ordered pairs of positive integers satisfy this. We can see that the only possible value is if 21 and 189, 1, or we can also have 21 and 189. So the answer is going to be 2. And this case also won't work because that would not have the LCM be 189. So the only case that will work is 189, 21, or flipping the two values. So the answer is just going to be 2. And that's how you solve this problem. And this problem is very unique in the fact that we have LCM AB, GCD AB, AB. So we can somehow manipulate the equation to get it all in terms of just two variables. And from here, we can just use Simon's favorite factoring trick. So this is a very cool idea to this problem. Okay, so now let's take a look at this next problem from the 2019 AMC 10A. So this, even though it may seem like a kind of combo problem, we can see that it has a really clever solution. A rectangular floor that is 10 feet wide and 17 feet long is tiled with 170 1-foot square tiles. A bug walks from one corner to the opposite corner in a straight line. Including the first and the last tile, how many tiles does the bug visit? So this is actually a really cool property about grids. So whenever you draw a line between 2 points in a grid, the number of squares it will pass through is given by the formula A plus B minus the GCD of A and B. And I'll explain why this is true in a moment. So basically, the reason that this formula is true, let's just take some examples. Don't worry about the formula for now. So look here at this point. So we start off at this point here, right? So how do we get to the point on the opposite side of the corner? Well, notice that we have to go in this small grid here. I'm not doing the 10 by 17 grid because that's a little bit of a more tricky case. So we have to go 5 to the right and 3 up in this case, right? So essentially, notice that whenever we go to another square that's to the right of it, so whenever we go to a square that's to the right of the current square, we add another square. We're essentially entering another square in our grid. And similarly, whenever we go up to another square, we're also going into another square, and we also have to add 1 to our count. So basically, each time you go right or up, we're essentially entering a new square. So basically, the number of times that we're going to actually go through this whole grid is just going to be 3 plus 5, except that when you reach the corner point here. So when you reach the very corner point right here, then we subtract 1. Because when we go to the corner point here, we're simultaneously moving to the next vertical edge and the next horizontal edge. So we're simultaneously moving to the right, to a point to the right, and a point upwards. So then we subtract 1. And this gives 7. But now what about in a 4 by 6 grid? In a 4 by 6 grid, it's slightly different. It's a similar idea. But in this case, notice that we pass through this another lattice point here. So now we have 2 lattice points that go up and to the right. So now we're essentially going to the up and right simultaneously in 2 places, not just 1 place in the braiding. So then in this case, or another way of thinking about it is you can imagine placing 2 by 3 grids. So you can imagine 2 by 3 grids like this. So you can imagine these 2 by 3 grids, and we're essentially going from one corner in each of the grids. So we just do 2 times for the 2 by 3 grid. So essentially for this case, we can see that we're going to do 6 plus 4, except we have to subtract 2 because there are 2 points in which we're going to the right and to the up simultaneously. Okay? And this is a total of 8, right? So we have 8 total squares we're going to pass through in the second grid. Now what about for this very last grid here, the 10 by 17, the one we're given in the problem? So for this last grid here, okay, so for this last grid, notice that it's a very similar thing. We're essentially drawing, let me just draw a line here. We're going forward 10 steps, to the right 10 steps, and upwards, to the right 17 steps, and up 10 steps. So that means we have 10 to 17. But then, just like earlier, we subtract 1, because there's 1 point where we're going to the right and up simultaneously. And this gives us 26. So in general, the formula is, if you didn't totally understand this, just apply the formula, a plus b minus the GCD of a and b. So for this problem, we can just do 10 plus 17 minus GCD 10 17, which is simply 1. So 26, the answer for this problem. And that's how you solve this seemingly obscure problem. And yeah, drawing a line through it and counting it would be super error prone. And I can imagine that being a really easy way to screw up. Okay, so now let's explore the Euclidean algorithm. Find the greatest common factor of 390 and 192 using the Euclidean algorithm. So basically what the Euclidean algorithm states is that the GCD of 2 numbers is the same as GCD of the number x and y minus multiples of the x. Okay, so I know this formula may seem a little bit complicated, but towards the end of the class, we're actually going to solve an IMO and USAMO problem using some of these techniques that we're going to learn today. So make sure to stick around for that. So as you can see here, we've got the greatest common factor of 390 and 192. So how can we find the value of that? The idea here is that the GCD of 390 and 192, GCD of 390 and 192 is just going to be equal to the GCD of 390 and the GCD of 390 minus 2 times 192, and then 192, right? Because by the Euclidean algorithm, the GCD of 2 numbers is the same as the GCD of the last number, and the GCD of 390 minus 2 times 192. That's what the Euclidean algorithm states. And you can do it for 1, you can do it for 2, you can even do it for 3. But in this case, we're just trying to get rid of, you just want to make the number small to the point where we can manually evaluate the GCD pretty easily. And then from here, this is just equal I'm not sure what happened there, equal to the GCD of 390 minus 2 times 192 is 390 minus 384, or 6. So now we can value the GCD of 6 and 192. But we're not done. We can apply the Euclidean algorithm yet again. And this gives us the GCD of, equal to the GCD of 6 and 192 minus 32 times 6. Because 192 is equal to 32 times 6. This is just equal to the GCD of 6 and 0. And what is the value of this? The GCD of a number and 0 is always just a number. So 6. So the greatest common factor of 392 and 192 is 6. And this is a very clever example of the Euclidean algorithm being applied to a problem. Okay, so now let's look at a problem from the IMO. And even though this is from the IMO, it's actually a pretty easy problem because it was from way long ago. So prove that 21n plus 4 over 14n plus 3 is irreducible for every natural number n. So basically what this is trying to tell us is don't get scared by the IMO problem. It's actually probably easier than most AMC 10 problems based on my experience. So we have to prove this is irreducible. So what does it mean by irreducible? It basically means it's in simplest form. So for example, 5 over 3 is irreducible. 7 over 4 is irreducible. But something like 6 over 4 is not irreducible because 6 over 4 is equal to 3 halves. So irreducible just basically means in simplest form. So basically the problem wants us to prove that 21n plus 4 over 14n plus 3 is in simplest form, basically. How can we do that? Well, if a fraction like 5 over 3 is in simplest form, that would mean the GCD of the numerator and the denominator has to be 1. Right? Because if the GCD of, well, in order for a fraction to be in simplest form, the GCD of the numerator and denominator has to be relatively prime. The numerator and denominator have to be relatively prime, or their GCD has to equal to just 1. So basically, we have to prove that the GCD of 21n plus 4 and 14n plus 3 is 1. And how can we do this? Well, the idea here is that the GCD of 21n plus 4 and 14n plus 3 is equal to 7n plus 1 and 14n plus 3. Right? Because, or actually, let me explain more. This is going to be equal to the GCD of 21n plus 4 minus 14n plus 3, comma 14n plus 3, right? That's the Euclidean algorithm we just learned. So now I have to prove this is equal to 1. And this is just nothing but GCD of 7n plus 1 and 14n plus 3. So now I have to prove that the GCD of 7n plus 1 and 14n plus 3 is 1. How can we do that? Well, notice that the GCD of this is just going to be equal to GCD of 7n plus 1, comma 14n plus 3, minus 2 times 7n plus 1. Right? This is just going to be equal to this. Right? Because we just use the Euclidean algorithm. And this simplifies to the GCD of 7n plus 1 and 1. Since this term here is just 14n plus 2. And 14n plus 3 minus 14n plus 2 is 1. So what is the value of the GCD of 7n plus 1 and 1? That's just 1. Since the GCD of any number in 1 is always 1. That's the greatest common factor they share. And if the GCD of the numerator and denominator is 1, that means it's irreducible. So now we are done, and we have done with the proof. So now you can tell everyone that you now know how to solve an IMO problem. But even though this IMO problem is way easier than anything you've ever seen on the IMO nowadays. Okay, so now let's take a look at our next problem. What is the largest possible value of n for which n cubed plus 100 is divisible by n plus 10? And I'm not directly going to apply the Euclidean algorithm here, but I'm going to use like a variant, something very similar here. So I'll give you some time to try this problem on your own. So basically, we have to prove that n cubed plus 100, not prove, we have to find the largest integer such that this is true. And this is equal to an integer. So I'll give you some time to try for yourself, and I'll give you some hints along the way. Yeah, some of you are saying 100 is not a cube. You cannot directly apply the formula here, but I'll give you a hint. You can apply it in some way. So it's not a cubed, but think about how you can try to relate it to a cubed. That's the hint that I'm giving. Somebody said polynomial division. Yeah, that could work, but there's an even easier way. Okay, so some of you are getting stuck here. So even when I saw this problem, I was like, 100. Yeah, that's not a cube. I thought the exact same thing you guys are thinking. But the thing is, this is equal to n cubed plus 1000 divided by n plus 10 minus 900 by n plus 10. So here's my hint. This is my hint. Try to use this. And then from here, we can use the formula you're probably thinking of. So basically, what we can see here is that we can express this in terms of n cubed plus 1000 minus 900 divided by n plus 10. The reason I express in this, you might be asking, is because I know n cubed plus 100 is the sum of two cubes. So I know by the sum of cubes formula that n cubed plus 100 is equal to n plus 10 times n squared minus 10n plus 100. Right? By the sum of cubes formula, we can break it down into these two factors. Right? So from here, we can see that n cubed plus 1000 divided by n plus 10 is an integer, right? So now, what can we do from here? So when will this be an integer? We already know n cubed plus 1000 divided by n plus 10 is an integer because we can express n cubed plus 100 in terms of n plus 10 by the sum of cubes formula. So now, when will 900 over n plus 10 be an integer? What is the maximum possible value such that it will be an integer? That's 890. 890 because if n is equal to 890, then the denominator is just 900, and 900 divided by 900 is 1. So 890 is the maximum possible value of n, such that 900 divided by n plus 10 is an integer. Because the maximum possible value of n plus 10 is just 900. And that's the solution for this problem. Simple, but it's very clever. Okay, now let's take a look at modular arithmetic. So this is going to be one of our main topic, the main topic for today. So basically, when a number actually introduced modular arithmetic back in the AMC classes, if you remember, and for modular arithmetic problems, if you remember when I introduced it back in the AMC classes, I never really introduced the formal mod notations. I never said something mod something. The reason is I didn't want to confuse people with the notation. But now that we're at the AMC 10-12 level, we need to actually learn the notation because it's much easier and there's many actual proper formulas that we can actually apply using modular arithmetic. So if a number n is a mod b, we say that the number n leaves the same remainder as a when divided by b. Basically what that means is, let's say we have 192 mod 3. Basically, 192 mod 3, the remainder of what 192 leaves divided by 3 is the same as the remainder when 189 is divided by 3. So 192 mod 3, we say it's equivalent or congruent to 189 mod 3. Right? Because 192 and 189 are the same mod 3. Because we just subtract 3. Because they leave the same remainder when divided by 3. And 189 mod 3 is also congruent, not equal to. Remember, it's congruent to 186 mod 3, which is also congruent to 183 mod 3. So basically, all of these numbers, 192, 189, 186, 183, they're all congruent to each other mod 3 because they leave the same remainder when divided by 3. And we can continue writing this, dot, dot, dot. all the way till 0 mod 3. Because, right, 192 leaves a remainder of 0 when divided by 3. So 192 mod 3 is the same, or equivalent, sorry, I should have said, is congruent to 0 mod 3. Because 192 leaves a remainder of 0 when divided by 3. 0 leaves a remainder of 0 when divided by 3. But we can also go in the other direction. We can also write it as congruent to negative 3 mod 3. Congruent to negative 6 mod 3. Basically, what this means is that negative 3 mod 3 is 3 less than a multiple of 3. So it's going to be the same as 0 mod 3. And negative 6 is 6 less than a multiple of 3, right? So negative 6 mod 3, since it's 6 less than a multiple of 3, it's going to be the same as 0 mod 3 too. So what does that mean? Well, we can continue writing this. So mods can also be negative. They don't necessarily have to be positive. Because if you think about a number being a multiple of 3, it's the same as being 3 less than a multiple of 3. And then we can also go the other direction too. We can go equal to 195 mod 3, etc. So basically what I'm trying to do here, I'm not actually solving a problem. I'm just illustrating the concept of mods. Basically, all these numbers, any number that's a multiple of 3 is congruent to 192 mod 3. Whether it's positive or negative doesn't matter. Any integer is going to be multiple of 3. Okay, so now let's move on to our first modular arithmetic formula. Basically, if A, and this is where mods start to actually get powerful. It's not just the dummy notation. We're actually using it for problems that would be much harder to solve without mod. So if A is x mod n, and B is y mod n, then AB is equal to xy mod n. So basically what that means is that if you have two numbers that are certain mod n, they're going to be equivalent when you multiply them. Basically, we can do multiplication in mod n. That's what it says. So how can we apply it to our problem here? Find the remainder when 347 times 643 is divided by 7. The idea here is that 347 is congruent to 4 mod 7, right? Because if you do 347, if you divide it out, we get it's going to be equal to. If you divide it out, we get it has a remainder of 4. So 347 leaves a remainder of 4 mod 7. So 347 we say is congruent to 4 mod 7. Similarly, we have 643 is congruent to, well, we can divide it out again. We can just do division. So we can, if you just write the division out, we can get that it's going to be congruent to 6 mod 7. So if 347 is 4 mod 7 and 643 is 6 mod 7, then 347 times 643 will be congruent to 4 times 6 mod 7. The reason is, you can think of it as 347 is 4 mod 7. 643 is also the same as 6 mod 7. And what is 24 times 6 mod 7? Also the same as 24 mod 7. Or 3 mod 7. Okay, so basically we see the remainder when 347 times 643 is divided by 7 is just 3. So here's another way of thinking about it. We can also think about it in terms of negative numbers, because it can actually help us avoid a second step. We can actually simplify and reduce a step by using negative mods. So basically, we can use and say that negative 4 is negative 3 mod 7, and 6 is negative 1 mod 7. So instead of writing 4 times 6 mod 7, having to do one extra step, we can write 347, which is 4 mod 7, or maybe I shouldn't just erase it. It's 4 mod 7 is also negative 3 mod 7. Similarly, 643 is 6 mod 7 is also going to be negative 1 mod 7. The reason is that if a number is 4 more than a multiple of 7, it will be 3 less than a multiple of 7 too. If a number is 6 more than a multiple of 7, it will be 1 less than a multiple of 7 too. So instead of doing 4 times negative 6, we can actually replace this with negative 3 times 1. And then we can eliminate this extra step. So we can just directly do negative 3 times negative 1, which is going to be 3 mod 7. So then we see it's 3 mod 7. And generally, we want to use negative mods when we're doing less than a certain multiple, and positive mods when we're closer to a little bit more than a multiple. We'll actually explore negative mods more in the rest of the class. So another very important property, if you have two numbers, a is congruent to x mod n, and then we know that a to the n is congruent to x to the n mod n. So here's a very simple example. 36 leaves a remainder of 1 when divided by 5, so it's going to be congruent to 1 mod 5. Right? So 36 to the power of 9 will be congruent to 1 to the power of 9 mod 5. It's as simple as that. Basically, in this case, we have m is 9, and a is 36, is the same as x, or 1 mod 5. So this is going to be 36 mod 9 is going to be congruent to 1 mod 5. Okay, so it looks like, okay. Now, we can do something very similar for this. 34, we know is going to be congruent to 4 mod 5, since it leaves a remainder of 4 when divided by 5, which is also going to be negative 1 mod 5. Since being 4 more than a multiple of 5 is the same as being 1 less than a multiple of 5. And basically from here, we can see that 34 to the power of 9 is just going to be negative 1 to the power of 9, which is going to be negative 1 mod 5. And negative 1 to the power of mod 5 is also 4 mod 5. So basically the idea here, the reason we used negative mod was because we saw that if we just wrote out, we know 34 is 4 mod 5, right? And if we just did 4 to the power of 9 from here, 4 to the power of 9, well, we could have multiplied that all out, but that would take a long time. So instead of doing 4 to the power of 9, we can see that 4 is also just negative 1 mod 9. So we can replace 4 with negative 1, and then it becomes a lot simpler. So this is a very powerful property, and generally, we want to use positive mods when they're just a little bit over a multiple, and negative mods when they're a little bit less than a multiple. Okay, so now let's look at our next fact, which is going to be Euler's-Totient theorem. So you remember from the Totient video that on this channel, basically what you can do from the Totient video, basically we have that a to the power of totient n. Remember the Euler's-Totient function that from the video is going to be equal to 1 mod n if and only if the GCD of a and n is 1. So this is the Euler's-Totient theorem, and actually this is a generalization of the Fermat's-Little theorem, but I think it's not really needed to introduce the Fermat's-Little theorem when Euler's-Totient is just pretty much a generalization of it. So basically, we have a to the power of the totient of a number is going to be 1 mod n if, this is a very important condition, if and only if the GCD of a and n is 1. This is a very important condition, don't miss this. So the idea is that 7 to the power of totient of 400 is going to be congruent to 1 mod 400. The reason is that we know that we always want to check for this condition. Is the GCD of a and n equal to 1? So is the GCD of 7 and 400 equal to 1? Yes, so we're good. So if the GCD of 7 and 400 is 1, now we know that this is true. 7 to the power of totient 400 is 1 mod 400. Now, if you remember from the totient video, we can find the totient of 400. 400 is just equal to 2 to the power of 4 times 5 squared. So the totient of 400 is just going to be equal to, well, we can just simplify this out. We multiply this by 1/2 and 4/5 to get that this will just be equal to 2 to the 5 times 5, which is 160. So then we can just replace the totient 400. Let me just say, totient 400 is 160. So we can just replace totient 400 with 160. So we know that 7 to the power of 160 is 1 mod 400. And that means that 7 to the power of 803 will just be equal to 7 to the power of, congruent to, not equal to the power of 5 times 7 cubed mod 400. And we know that 7 to the power of 160 is just 1 mod 400. So this is going to be congruent to 1 to the power of 5 times 7 cubed mod 400, which is just 343 mod 400. So the answer is just 343. And the idea here is that we can always find a number, 7 to the power of totient of the number is 1 mod n. And then from here, we can just see that it's just going to be 7 to the power of 160 to the 5, because that means we know that 7 to the power of 800 is just going to be 1. And then we're going to multiply by 7 cubed. So that's the idea for Euler's-Totient theorem. Okay, so now let's try another problem using Euler's-Totient theorem. So basically, you have an integer n selected in this range from 1 to 2020. What's the probability that n to the 16 has a remainder of 1 and divided by 5? So basically, what's the probability n to the power of 16 is 1 mod 5? So how can we do this problem? Well, let's look to our handy Euler's totient theorem. Basically, we know that n to the power of totient 5 is just going to be congruent to 1 mod 5. Right? By Euler's totient theorem. And what is totient 5? Well, totient 5 is just going to be 5 times 4/5, which is 4. So totient of 5 equal to 4. So now we know that n to the power of 4 is just going to be equal to 1 mod 5, or n to the power of 16 will just be equal to 1 mod 5. Oh, it will be equal to 1 to the power of 4 mod 5, which is just 1 mod 5, because 1 to the power of 4 is just 1. So if n to the 16 is 1 mod 5, this is not always going to be true. It's only going to be true if the GCD of n and 5 is 1. Remember, the condition, this is very important. If and only if the GCD of a and n is 1. So in this case, if and only if the GCD of n and 5 is 1. Okay, so when is the GCD of n and 5 going to be 1? The GCD of n and 5 will be 1 if and only if n is not a multiple of 5. So from here, it's pretty straightforward problem. There's 20 numbers from 1 to n. 404 of those numbers are multiples of 5. So the probability of picking a number that's not a multiple of 5, or that will have this equation be true, is just going to be 2020 minus 404. Because if it's a multiple of 5, then it won't work. Divided by 2020, which is 1616 over 2020, or 4/5. Which is the answer for this problem. So now let's look at the Chinese remainder theorem. Basically, what the Chinese remainder theorem states, is that the smallest number that leaves remainder, basically let me just explain the Chinese remainder theorem with an example. Basically, we have this number x that is congruent to 11 mod 13, and that is also congruent to 2 mod 5. Right? So basically what the Chinese remainder theorem states is that there will be a unique solution for x modulo 65. So basically, if you have a value of x mod 5 and mod 13, there's going to be a unique solution mod 65. The reason being is that always going to be, sorry, not 60, let me make it clear. There's going to be a unique solution modulo 13 times 5. If and only if 13 and 5 are relatively prime. So basically, if our two bases are relatively prime, then we know it's going to be congruent to mod 4, 65. Because if 13 and 5 are relatively prime, then we can see that by the Chinese remainder theorem, it's going to be mod 65. So from here, what do we see? Well, from here, we can see that there's a unique solution modulo 65. So how can we find a solution? The first strategy, the somewhat bashing strategy, is just to look at the possible values of x. So x can either be 11, 14, 27, 40, or 53. Because it has to be less than 65. So now we just check. Which one of these values also is 2 mod 5? We can see that 11 is not 2 mod 5, 14 is not 2 mod 5, but 27 is. So you can see that the answer is just going to be 27 modulo 65. Sorry, it should be 37. Should be 37, sorry. So 37 is the first solution that works, so it's going to be 37 mod 65. So the answer is just going to be 37. And that's the solution for this problem. So basically, the Chinese remainder theorem states that if you have two modulos that are relatively prime, there's going to be a unique modulo that's the product of the two mods. Okay, so now let's take a look at the next problem. Okay, so this is a very clever problem. So I'll give you some time to try this for your own. So basically, we have to find the 10th digit of this number. So I'll give you some time to try, and I'll give you some hints along the way. And also, by the way, I forgot to mention the previous problem. There's actually a faster way of calculating modulos for large values of mods, but I think that's a bit too complicated for this class, so maybe I'll cover it in advanced class in the future. But the technique for that, calculating two mods for higher values, is actually covered in Introduction to Number Theory book. So definitely get that book. And okay, so it looks like some of you are looking at some good ideas. So basically, just ignore this 2017 term, where you can just, it's not that hard, but you can just subtract it at the end. So let's find the value of 2015 to the power of 2016 mod 100. Because if you think about it, in order to find the 10 digits of a number, we really just need the last two digits. So we can just find the number mod 100. So how can we find 2015 to the power of 2016 mod 100? Well, notice that 2015 is congruent to 15 mod 100. So 2015 to the power of 2016 is just going to be congruent to 15 to the power of 2016 mod 100 by our mod properties, right? Okay, so now what? Now we think. So I'm going to show you two solutions now. One using Chinese remainder theorem, one without. So let's first do the regular solution without Chinese remainder theorem. What we can do is by Euler's Totient theorem, we have that 15 to the power of Totient 100 is congruent to 1 mod 100. Right? This is a straightforward application. But actually, this is not true. This is actually not true. The reason is that 15 and 100 are, the GCD of them is not 1. The GCD of, remember, whenever you use Totient theorem, Euler's Totient theorem, no, Euler's theorem, not Totient theorem. The GCD of 15 and 100 has to be 1. But in this case, it's not true. And that means that's not good. So that means this is false. So this doesn't work. This method actually doesn't work. So now we're going to move to a better solution. And some of you are actually just saying, listing it out, looking for a pattern. Yeah, that does provide a valid solution, I think. But it's a little bit more complicated. I'm going to show you a very simple solution using the Chinese remainder theorem. So basically, what is 15 to the power of 2016 mod 100? Well, something to notice here is that in order to find the value 15 to the power of 2016 mod 100, you can also find the value of 15 to the power of 2016 mod 25 and mod 4. Reason being is that 25 times 4 is 100. But be very careful here. We can only split up mods by the Chinese remainder theorem if our mods are relatively prime. Very big emphasis on that. Just like Euler's Totient theorem failed in this case, make sure to remember that we can split it up into mod 25 and mod 4 by the Chinese remainder theorem. So basically, let's say we had mod 9, but you cannot just split it up into mod 3 and mod 3. Because 3 and 3 are not relatively prime. So that doesn't work. But if you had like mod 10, you can split it up into 5 and 2 since 5 and 2 don't share any common factors. In this case, we can split 100 into 25 and 4. Since 25 and 4, they're both relatively prime. So we're good here. Okay, so what is the value of 15 to the power of 2016 mod 25? This is just going to be congruent to 0 mod 25. The reason is that 15 is a multiple of 5, right? 15 is a multiple of 5. So when you do 15 to the power of 2016, we're doing 5 times 5 times 5 times 5 so many times. So obviously, it's going to be a multiple of 25. Of course, it's going to be a multiple of 25 or 5 squared. Because it's going to have a factor of 5 to the power of 2016. Because 15 is a multiple of 5. So 15 to the power of 2016 is a multiple of 5 to the power of 2016. So clearly, it's going to be congruent to 0 mod 25. But now we also know 15 to the power of 2016 mod 4. Well, 15 is congruent to 3 mod 4. So then, this is congruent to 3 to the power of 2016 mod 4. So then we can find the value of 3 to the 2016. We can multiply 3 2016 times. Or we can do something even smarter. Clearly, yeah, you're not going to have fun multiplying 3 2016 times, especially in a 75-minute time limit. So instead of doing that, let's replace 3 with -1. So this is those cases where we're going to use negative. Because it's 3 mod 4 is the same as just 1 less than a multiple of 4. So this will be congruent to -1 mod 4. So then, 3 to the power of 2016 is just going to be negative 1 to the power of 2016 mod 4. And negative 1 to the power of 2016 is just going to be congruent to 1 mod 4. Right? Because negative 1 repeats in cycles. Negative 1, 1. Negative 1 to the power of any even exponent is just 1. So now we know that our number is 1 mod 4. Let me just box or underline them. 1 mod 4 and 0 mod 25. So now we can find a solution by the Chinese remainder theorem. So if we know our number is 1 mod 4 and 0 mod 25, we can see that we can find a solution modulo 100. So, and we have 0 mod 25 too. So you can see that we can just list a few values, 0, 25, 50, 75, all the values less than 100. Which one of these leaves is 1 mod 4? 25. 25 is 1 mod 4 and 0 mod 25. So we can see the solution to this modulo is just going to be 25 mod 100. So if a number is 1 mod 4 and 0 mod 25, we know the number will be 25 mod 100. Okay, so if a number is 25 mod 100, then this expression here is just going to be equal to 25 minus 17, which is 0, 8. So the 10th digit of this number is just going to be 0. So the answer is just going to be 0 to this problem. Because you know the last two digits are 25, so we do 25 minus 17 is going to be 8. And even though it took a long time to explain this problem, really it's pretty simple. If you just think, oh, mod 25, mod 4, mod 25 is 0, mod 4 is just negative 1 to the 2016, which is 1. So it's really a pretty simple problem once you get the hang of applying the Chinese remainder theorem. Okay, so now let's take a look at our prize for today. So you can fill out the raffle form. It will be in the chat. Today we'll be raffling a daily challenge course by Potion Low and a Wolfram Notebook subscription with $66 value. Also, the raffle winners for last week will be announced. I'll see you all in a few minutes. And I'll show you a problem. I'll show you another problem to work on. And the next problem I'm going to show you is going to be very clever. mentioning some of you are mentioning some good ideas in the chat. To get mod 45, you need mod 5 and mod 9. And mod 5 is pretty easy to find. So now the real question is just finding mod 9. And that's the tricky part of the problem. And there's two ways to find mod 9. One is the way, a little bit more complicated way. One is a really nice, clever way. And then from there, you can use Chinese remainder theorem. So I'll explain the solution in a few minutes after our break is over. But for those of you trying the problem, that was a hint for you guys to hopefully get some ideas how to move forward. Okay, so now let's resume. Okay, so some of you had some great ideas in the chat. So we have this large number n, 79-digit number, with the numbers 1 through 44 in order, one after another. So in order to find the remainder when n is divided by 45, in order to find n mod 45, we need to find n mod 5 and n mod 9, right? Because 5 and 9 are relatively prime. Right? We can split it up into these two terms. So what is n mod 5? This is pretty easy. N mod 5 is just 4. So n is congruent to 4 mod 5. Right? The reason is that if the last digit is 4, so that means it's going to have a remainder 4 when divided by 10 or 4 divided by 5. That's a pretty easy case. I'm sure you all can do that. But the tricky part of the problem is n mod 9. And in order to do that, we need to look at the sum of digits of n. Okay, so there's actually two ways to do that. And basically, we just split n mod 45 into n mod 5, n mod 9. So there's actually a really clever way. So one way is just sum all the digits up. We can just group it into, this is actually the way I solved it the first time I solved this problem. I did 1 plus 2 plus 3 all the way till 9. And then I did 0, 1, 2. I just looked at find the sum of all the unit digits, and then found the sum of all the tens digits and added them up. And that is a perfectly good way to solve the problem. And it works fine. But there's an even cooler way to do this that I did not think of myself when I first tried the problem. Basically, the idea here is that in order to find the sum of the digits mod 9, well, we need to just find 1 plus 2 plus 3 plus 10 plus 11, or plus 1 plus 0 plus 1 plus 1 plus dot 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 plus 4 plus 3 plus 4 plus 4 mod 9, right? We just need to find this. This is the sum of the digits. So notice that 1 plus 0 mod 9, 10, right? We have 1 plus 0. We're adding the digits up. So what we can do instead of just adding the digits up is we can say that this is going to be congruent to 1 plus 2 plus dot 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 plus 10. 1 times 10 plus 0 plus 1 times 10 plus 1 plus 4 times 10 plus 3 plus 4 times 10 plus 4 mod 9. The reason is that you might be a little bit, basically for all the tens digits of all the numbers, rather than just adding them up, I multiplied them by 10. Because a number mod 9 is the same as a number mod 10. Because let's say we have a number x, the tens. So we're basically looking at all the tens digits. The number tens digits mod 9 is the same, is congruent to the tens digit mod 10 times the tens digit. Because you can think about it that this is going to be congruent mod 9, right? Because the reason this is true is because that means that 9t is congruent to 0 mod 9. Because the difference of t and 10t is 9t, which is a multiple of 9. So t and 10t is congruent mod 9, meaning that a number is the same as the number times 10. So basically what I'm doing is looking at all the tens digits, looking at all the tens digits up, and I'm saying that multiply by 10. Because if I multiply by 10, now it's the same mod 9. So These two are the same mod 9. No, now what is this last expression mod 9? Notice that 1 times 10 plus 0 is 10 mod is 10. 1 times 10 plus 1 is 11. This is 43. 44. What does that mean? Well, that means that the sum of the digits of this big expression is the same as just 1 plus 2 plus 3 all the way till 45 mod 9. Because of the 10-digit property I just explained. Sorry, till 44, not 45. And what is this value? This is just going to be 44 times 45 by 2 mod 9, which is just 0 mod 9. Since this is just going to be 22 times 45, which is a multiple of 9. Right? So this is really clever. So if a number is 0 mod 9 and 4 mod 5, then the number will also be equal to. So then we can just write the possibilities. 0, 9, 18. Oh, we see that 9 is... Oh, we immediately see that 9 works, since 9 is 0 mod 9, and 9 is also 4 mod 5. So you can see that the solution is just going to be 9 mod 45. So the remainder when n is divided by 45 is just going to be 9. And that's the answer. So this is clever. So this is a little bit tricky. Basically, the idea was we use CRT, we split n mod 45 to n mod 5 and n mod 9. Then we found n mod 5 pretty easily. But then in order to find the sum of the digits, rather than evaluating it by doing the grouping method, we can essentially write it as 1 times 10. That all the 10 digits as the 10 digits times 10. So we can rewrite it as this number here, which is just 0 mod 9. And that's a very clever solution to this problem that even I did not think of when I first did this problem. So the answer is just going to be 9. Okay, so hopefully that solution was clear and it was a cool idea. But now let's take a look at this next problem. And this next problem is very easy comparatively to the previous one. So basically, what is the 100th digit of 20 factorial minus 15 factorial? So I'm not going to go too much into this since the problem is pretty easy. Basically, we really just want to find 20 factorial mod 100 and 15 factorial mod 100. Right? So what is 20 factorial mod 100? 20 factorial mod 100. Well, notice that, sorry, not 100, 1,000. The reason is that in order to find the 100th digit of a number, we need to look at the last 3 digits of the number. Since the last 3 digits consist of the hundredths, tenths, and ones digit. So let's look at the last 3 digits of the number. So what is 20 factorial mod 1,000? And what is 15 factorial mod 1,000? And then we just subtract them. So 20 factorial mod 1,000 is just going to be 0 mod 1,000. Because, note that 20 factorial by Legendre's formula, 20 factorial will have 20 divided by 5. Oh, it looks like here, yeah. Okay, so it looks like some of you had a question about why this is true. So basically, let's take an example 37. 37 is 1 mod 9. Leaves a remainder of 1 when divided by 9. And 37 is also 3 plus 7 is also going to be equal to 10 or 1 mod 9. So you can see that they're actually equal in this case because 30 is the same as 3 mod 9. 30 minus 3 is congruent to 0 mod 9. Basically, that's the idea. Okay, so now let's go back to the problem. So if you were still confused in this problem, just take in a few examples and hopefully that should make it clear about why this property is actually true. So basically, in this problem here, we can see that 20 factorial is going to be 0 mod 1,000 because 20 divided by 5. So 20, because 20 factorial has 4 factors of 5 in it by Legendre's formula, right? We just do 20, the floor of 20 divided by 5 is equal to 4. But now we can see that, so we can clearly see that 20 factorial is a multiple of 5 to the power of 4. So, and if 20 factorial is a multiple of 5 to the power of 4, it's also clearly going to be a multiple of 2 to the power of 4, since 20 has way more than 4 factors of 2. So now we know that 20 factorial will have 4 factors of 5 and way more factors of 2. So 20 factorial is clearly a multiple of 1000. Similarly, we have 15 factorial, which is going to be 15 divided by 5 equal to 3 factors of 5. So 15 factorial also has 3 factors of 5, and will have way more than 3 factors of 2, because clearly it's going to have way more than by Legendre's formula. So we can clearly see that 15 factorial and 20 factorial are both 0 mod 1000. So their difference is just also going to be 0 mod 1000. So the answer for this problem is just going to be 0. Because the difference of 0 and 0 is just 0. So our number, or let me just be a little bit clearer. So our number is just going to be 0, 0, 0. Our last 3 digits are just going to be 0, 0, 0. So clearly the 100 digit is just going to be 0. And that's the solution for this problem. Okay, so now let's take a look at this problem. Oh, this one is very cool. Let Sn equal the sum of the digits of that positive integer n. For example, we add the digits up of this number, sure. For some n, we have S of n is 1274. Which of the following could be a value of S of n plus 1? Okay, so I'll give you some time to try this on your own. Try this problem on your own, and I'll come back to you with the solution in some time. So basically, yeah, I'll just let you try. Okay, so now let's start. The answer for this problem is actually 1239. So let me explain why. So basically, take a number 18, for example. When we increase the number 18 to 19, the sum of the digits increased by 1. The sum of the digits increased from 9 to 10. Right? But what if we take a number 19? So if we add 1 to 19, now we have the number 20. So now the sum of digits of 19 was 10. But when we added 1, now the sum of digits only became 2. But basically the idea here is whenever we increase the number by 1, we're increasing the value by 1. But sometimes when we carry over, so basically when we do 19 plus 1, we do 0 and make it a 1. So instead of having 10 in one place value, we move it to 1 in the next place value. So overall, the sum of the digits by carrying over becomes 9 less. So no matter what, when we add 1, the sum of the digits will increase by 1 and sometimes decrease by 9, or times multiple 9s even. So basically what this means is that we are always increasing our S. So S of n plus 1 is always going to be 1 more than S of n mod 9, because you could also decrease by 9. So basically that means that S of n plus 1 has to be the same as 1275 mod 9. And 1275 is just 6 mod 9. So which of these option choices is 6 mod 9? 1 is not, 3 is not, 12 is not, 1239, we can see that it is 6 mod 9, and this is not. So the answer is D, because D is the only option choice such that it's going to be the same as 1275 mod 9. Because remember, when we carry over, we're reducing the value by 9, but when we're typically we just add 1, but sometimes, or we might carry over and reduce our sum of digits by 9 or even multiples of 9. So no matter what, we're always going to increase it by 1 mod 9 every time. So our answer is simply 1,239. So now let's take a look at Diophantine equations. Okay, so for how many ordered pairs of integers x and y satisfy the equation x to the 2020 plus y squared is 2y? This is another cool problem. And basically what a Diophantine equation is literally it's an integer equation. Any equation with integers is a Diophantine equation. So Diophantine equation is somewhat like a miscellaneous topic. But in this last section here, we're actually going to explore a USAMO problem that uses Diophantine equations. But it's very clever, and it has a very, very cool solution. You should definitely stay till the end to hear how to solve such a hard problem but using a very simple technique. Okay, so for this problem, the idea here is that let's consider the different possible values. So a realization to come across is that let's try some values. We know it has to be integers, which means it's the Diophantine equation. So what if x is 0? Because this term seems like a big weird term here. This weird term here. This term seems really weird. This is the only like awkward term. X to the power of 2020. That seems very insane. So let's see, what are the possible values of x? Okay, so if x is 0, now we have 0 plus y squared is 2y. And that means that by solving the quadratic, we learned in the first class, polynomials, y can either be 0 or -2. Sorry, 0 or 2. Right? It's simple quadratic stuff. But now what if x is 1? If x is 1, now we have 1 plus y squared is 2y, or y squared minus 2y plus 1 is 0, or y minus 1 squared is 0. Which means y is 1. So y is 1 is the only solution in this case. Now what if x is 2? Now this is where things get a little bit tricky for this problem. So if x is 2, now we have 2 to the 2020 plus y squared equal to 2y. Okay, so is this even possible? Is there any solutions here? Well, what I'm going to do is I'm going to try solving this quadratic. So I'm going to do y squared minus 2y plus 2 to the 2020. And this is just going to be equal to, we can solve the quadratic by the quadratic formula, plus or minus square root of b squared minus 4 times 2 to the 2020. Oh no, 2 to the 2020 is so large that this discriminant of the quadratic is negative. So this discriminant of this quadratic is negative in this case. So clearly this doesn't have any real solutions to it. So since the discriminant of this quadratic is negative, there are no real solutions to this equation. And you may be asking, why is this true? The reason is that, well, this can never be 0. Because the maximum possible value of 2y minus y squared, the reason this can never be 0 is because 2y minus y squared, if you remember from the first class, we learned completing the square. So this is just going to be equal to, by completing the square, negative of y minus 1 squared plus 1. So essentially, we see that the maximum possible value to this expression is 1. So no matter what, 2y minus y squared is going to be at most 1. So there's no way 2y minus y squared can be equal to 2 to the power of 2020. So clearly x equal 2 case doesn't work. So you might actually think, oh, now we're done, right? Now we found the value of x equals 0 and found the value of x equals 1. Now we just have 2 cases. And that was a very common silly mistake. But remember, we have integers, not necessarily positive integers. So x could be, for example, -1. This is a tricky part. Make sure always remember negatives. Unless this problem says positive integers, don't forget the positive word. Make sure to always be either for positive, non-negative, integer, whatever, natural, whatever numbers there are. Be on the lookout for them. So x equals to -1. Does that work? Well, we see that that's just the same thing. We'll have the same thing. 1 plus y squared equals 2y. So have the same solution as this x equals 1 case, y equals 1. And x equals -2 will have the same solution of, x equals -2 is also going to be the same. 2 to the 2020 plus y squared is 2y. This again, as we found in the x equals 2 case, will also have no solutions. So this is no solutions. So 0 solutions here, 1 solution here, 2 solutions here, 1 solution here, and 0 solutions here. Overall, we have if you add them up, we have a total of 4 solutions, and that's the answer for this problem. Okay, now let's take a look at the next problem. This is a really cool Diophantine equation problem. So we're multiplying m squared times n, and we want to equal to 20 to the power of 20. That's interesting. Okay, so how can we do this problem? Okay, so I'll give you some time to try this. So m squared n equals 20. Let me just see. Oh yeah, so this is our second to last, or maybe more problems, but. So this is really clever. So I'll give you some time to try this. Oh yeah, I think I was a little bit unclear here. I'm looking at some of the messages. Yeah, any value of x 3 or more, or any value of x -3 or less, those also won't work. Since just like earlier, it would be way too large. 3 to the 2020 would be even larger than 2 to the power of 2020. So clearly, none of the values x equals 3 or more, or x equals -3 or less will work. Since just like earlier, maximum value 2i minus y squared is 1, so it can't ever be equal to 2 to the 2020 or anything larger. So for this one. Okay, so here's the idea. We're multiplying a perfect square by a number. So we're multiplying m squared n, and you want it to equal to 20 to the power of 20, which is just 2 to the power of 40 times 5 to the 20. Right? Okay, so what do you notice on the left-hand side and the right-hand side? Clearly, 2 to the 40 times 5 to the 20 is a perfect square. Clearly, m squared is also a perfect square. So if 2 to the 20, if this right-hand side is a perfect square and this m squared term is a perfect square, what must be true of n? N also has to be a perfect square. Because if m squared is a perfect square, if the right-hand side is a perfect square, n has to be a perfect square. Let's just say that n is p squared. Then this means that m squared p squared is 2 to the 40 times 5 to the 20. Or this means that mp is simply 2 to the 20, 5 to the 10. So now what can we do? Well, now let's just take a few examples. If m is equal to, let's say, 2 to the 5 times 5 to the 3, then n will be equal to 2 to the 15 times 5 to the 7. If m is equal to 2 to the 20 times 5 to the 3, n will be equal to 2 to the 0 times 5 to the 7. Let's take one more example. If m is equal to 2 to the 0 times 5 to the 0, n can be equal to 2 to the 20 times 5 to the 10. Basically, what we're seeing is that for any m that's a factor of this value, there's going to be a valid solution to our equation. For any m that's a factor of 2 to the 20 times 5 to the 10, we're going to have a valid solution to our equation mp equals 2 to the 20 times 5 to the 10. So clearly, the number of factors of 2 to the 20 times 5 to the 10 is just our answer. Because for any value of m that's a factor of it, we can find a corresponding value of, sorry, I don't know why I wrote p here, I meant to write p here. Corresponding value p such that our equation is held true. So clearly, how many factors are there of this? By our factor formula from the AMC 8 classes, we have 21 times 11 equal 231. So clearly, the answer to this problem is simply 231. And that's the solution for this problem. Okay, so now we're going to move on to the USAMO problem, like I said in the beginning. And even though this is USAMO, again, it's not that hard of a problem. It has a very nice and clever solution. Even though it may seem complicated, this is a really cool solution. You definitely don't want to miss it. It's a really clever way. So basically, we have n1 to the power 4th plus n2 to the power 4th plus ... plus n14 to the power 4th to the 4th power. It's 1599. So in Diophantine equations, another strategy is that you take certain mods. So we can combine Diophantine equations in modular arithmetic. So whenever you have some Diophantine equations, generally by taking mods, we can simplify and cancel out the bulk of our terms. So what mod do we take? So basically, we can take some mods to get rid of terms. So notice that this is just going to be equal to, notice that 1599 is so close to 1600. 1599 is so close to 1600. So I'm just going to have to rewrite this as 1600 minus 1. Because that's like really the only thing that seems logical here. Right? So what mod can we take so we can cancel out a bunch of terms? So what mod can we take to just eliminate a bunch of terms and just be left with some simple stuff? The idea here is taking mod 16. If you take mod 16, we get n1 to the 4th plus n2 to the 4th plus n14 to the 4th. This will be congruent to -1 mod 16. Right? Okay, the reason is that 1600 is a multiple of 16, -1 is -1 mod 16. So if we take mod 16 to this whole equation, it's just going to be -1 mod 16. Right? Because the reason we want to take mod 16 is because now we're getting rid of the 1600. 1600 just goes away. Okay, so now what? Well, now, -1 mod 16 is nothing but 15 mod 16. Oops. So now we can just make this 15 mod 16. Okay, so now what is n1 to the power 4 mod 16? So whenever we take a number to the 4th power, mod 16, it's always going to be 0 or 1 mod 16. Because whenever you take a number to the 4th power, it's always going to be 0 or 1 mod 16. The reason is, let's say let's not say n. Let's say n is even. So if n is even, then n to the power 4 will be a multiple of 16 or 0 mod 16, clearly. Right? Because if n is even, it's a multiple of 2. So then n to the power 4 will be a multiple of 2 to the power 4 or 16. Thus, it will be 0 mod 16 if n is even. Now, if n is odd, let's look at the different possibilities for if n is odd. Because if n is odd, we can see that n to the 4th will be 1 mod 16. Okay, so if n is odd, we see that if n is, okay, so if n is 1 mod 16, then n to the 4 will be 1 mod 16 too. So 1 to the 4 is equal to 1 mod 16. 3 to the 4 is 81, which is also 1 mod 16. 5 to the 4 is 625, which is also equal to 1 mod 16. And we can do the division out. 7 to the 4 is 2401. 49 squared, which by the squaring trick is 2401. So, and we know that 2401 is also 1 mod 16. 9 to the 4 is -7 to the 4, or 7 to the 4, because -1 to the power 4 is just 1. 7 to the power 4 is simply 1 mod 16. Similarly, for all other values, 11 to the power 4, 13 to the 4, and 15 to the 4, they're all always going to be 1 mod 16. Therefore, we see that n to the power 4 is always 0 or 1 mod 16, meaning that the sum of n1 to the power 4, n2 to the power 4, all the way till n14 to the power 4 is just going to be equal to some number between 0 and 14 mod 16. Basically, the maximum possible value of n1 to the 4, n2 to the 4, all these till n14 to the 4 is 14 mod 16. So 14 mod 16 can never equal 15 mod 16. Basically, this left-hand side here, n1 to the 4th will be 0 or 1 mod 16. This will be 0 or 1 mod 16. This will be 0 or 1 mod 16. Each of these terms will be 0 or 1 mod 16. So all 14 terms will be some number between 0 and 14 mod 16. And any number between 0 and 14 mod 16 can never equal to 15 mod 16. So it's a contradiction. That means we cannot have any solution whatsoever. Okay, so that's the solution for this problem. There's no solutions, and really clever trick of taking mod 16. And this is nothing close to the difficulty of anything you'd ever see on the USAMO today, or even the USAMO. So even though this is a USAMO problem, it's still much easier than anything you see today. But nonetheless, it's still a very nice problem in the sense that 1600 minus 1, we want to take mod 16 because then we eliminated the 1600 term, and we're just left with 15 mod 16, which is simple. And we can see that each of the n1 to the 4ths will just be 0, 1 mod 16, meaning that the sum of all of them is just going to be 0 to 14 mod 16. Okay, so that was a brilliant solution to this problem. Okay, so now we have I have some extra problems here. I'll skip this one. It might be in your, it'll probably be in your homework. Let's do this problem. This is a lot easier than the one we did earlier. But these other problems had a really nice solution. But now let's get started with this problem. How many of the first 2018 numbers in the sequence are divisible by 101? Basically, each of these terms can be expressed in the form 10 to the power of n plus 1, right? Okay, so the reason we express it in this form is because we've got a bunch of these random terms, so really the only way I could see this being useful, or the only way we can actually really generalize it for all these values for all the way till 2018 is just write it in exponential notation. 10 to the n plus 1, right? So we have to find when will this be divisible by 101. So when will this be congruent to 0 mod 101? Sorry, 101. When will this be true? Well, the idea here is that it will be 0 mod 101 when 10 to the n is negative 1 mod 101. Right? So when will 10 to the n be negative 1 mod 101? 10 to the n will only be negative 1. Well, clearly 10 to the 2 works. Clearly n equals 2 works, right? If that's not already clear, 10 squared is literally 101 is obviously divisible by 101 because 10 to the 2 is 100 and 100 is negative 1 mod 101, right? Because 101 is going to be always 0 mod 101. So if 10 to the n is negative 1 mod 101, if and only n is 2. So we know 10 squared is negative 1 mod 101. We can see that 10 to the 4th is going to be negative 1 squared mod 101. Or 1 mod 101. Ten to the power of 6 power is going to be negative 1 cubed, which is again negative 1 mod 101. We can continue this process. 10 to the 8 will be 1 mod 101. I'm just going to write 1 for now. 10 to the 10, again, will be negative 1. So basically, it will always be negative 1. Our condition will always be true if n is 2 mod 4. So if n is 2, 6, 10, 14, etc. So only if n is 2 mod 4 will this be true. As you can see here, right? And of course, the odd values won't work. So how many possible values of n are less than 244? Well, you can clearly see that the first 2018 numbers will range from n equals 2 all the way till n equals to 2019, right? Because 2018 numbers, 2 to 2019. So thus, we must have 2, 6, 10, all the way to 2018 are the numbers that work. So you can clearly see that a total of 2016 by 4 plus 1 equal to 505 numbers do work. And that's the solution for this problem. 505 is the answer. So the key idea was to write it in mod, and then simplify it, look for a pattern, and see that only if n was 2 mod 4 will it actually work. And then we can count that pretty easily using counting arithmetic series. Remember, this is like an arithmetic series from 2 to 2018. It will have 2016 divided by 4 plus 1 equals 505 terms. And that's the solution for this problem. Thank you for coming to this class. I hope to see you all next class where we'll start geometry.